Okay, so I see I'm moving around there, so I know that I'm live. So on the screen, you'll see that there's a video window on the left-hand side, and on the right, there are two virtual gauges. So what a virtual gauge is a computer top representation of a gauge that's live in the room. We've got one gauge over here, and we've got one gauge over there, and we're going to be using them for various purposes. So you can actually see exactly what I do on the gauge, on the virtual gauge, 100% clarity, so we don't have to rely on the video. But let's just pick up one of these and find out which one we should be working. So on this gauge, you'll notice on the screen it says 400263. That's the serial number of the gauge on the back. You can't see it, but it's a little bit too small. I guess my technical staff didn't realize that I needed a little bit more space to work with than what this wire would allow me, but anyway. The first part of our presentation, we're going to be talking about gauge check using the umbilical. So this is the umbilical that comes with this gauge, and the gauge on the screen that we're messing with is the one on the right-hand side, and you'll notice that if I was to plug the green one into the other side, that I would actually get a pressure. So whatever appears on this gauge is actually appearing on the screen. So the first thing I wanted to show you is how to check your gauge and check your tubes at the same time. Now, on this gauge here, we're showing CFM. So I want to compare pascals and pascals. And you notice I got 261, 262 on both channels. So that indicates that the channels are reading correctly and there's no leakage between the channels. So here I'm checking positive to positive. So I'm going to disconnect that. I'm going to go positive, negative. And you'll see that that seems to be okay. Now I'm going to go negative to negative. So I've pretty thoroughly checked those two gauges on both ranges. And now I'm going to test the yellow tube to make sure the yellow tube is not blocked or leaks. And there we're checking the yellow tube and we notice it leaks. If we were to get a little razor blade and just put a tiny little cut in that tube, you notice that that pressure would drop off very, very rapidly. You can also check this gauge between this gauge and another gauge to make sure that, in fact, we can do that right now. We can check this gauge here against this gauge over here. And we have to change this to pascals, of course. So 224, 225, it means this gauge is the same as that gauge. We can check the other channel in the same way. So we've got 204, 205. So this is meaning that both of these gauges are in good shape. I know there's a lot of talk about getting gauges calibrated on a regular basis. I think that's a lot of wasted time and money. And a gauge check should be something that gets performed on a regular basis. So that takes care of the gauge check part. So the next thing I wanted to talk about briefly was the difference between a pitot tube and a static probe. This is something that people get wrong all the time. Unfortunately, I'm kind of tangled up in my wires here. Just a minute, let me get these untangled so that okay, so we'll just put that over there so we've got some room to play with. Okay, so this is a static pressure probe here, and it has only one connection on it. So it's for measuring static pressure, and it's got 4 holes around the outside here so that no matter which way the air is blowing at it, it's just going to pick up the static pressure, not the background and not the velocity pressure. Now, a pitot tube, by contrast, has got 2 connections, one that goes to this little hole here that's meant to face upstream into the airflow, so it gets the velocity pressure, and then holes around the outside that pick up the static pressure. So this is something you can use to measure velocity. This is something that you use to measure static pressure. It's a common mistake that people seem to get those two things confused. So the next thing we're going to do is we're going to do a calibration check on this fan. And there we go. We're going to do a calibration check on this fan. We've got this blower door mounted inside a simulation chamber. So we're just going to hook the tubes up here. And to do this, a really easy way to do this is to use EQLA. I like to test at 25 pascals, so we're going to change the settings on here to effective leakage area, EQLA, and we're going to do this at 25 pascals. So we're going to set the pressure, just change that to the device that I'm on here, which is the 1000 fan. The range I'm on is C1, so that's C1, which is that one there. I got C8, C1 is that one there. Okay, so I'm on the right range, and so now I want to set pressure to 5, enter. So we've set the pressure to 25 pascals. You can do it at any pressure, but 25 pascals is a good pressure. And we've got an equivalent leakage area of 20 square inches. Now, you may not be able to see this, but if you look through this window here, you can see on the other side, we've got one of the sliders set to a 4x4 hole, 16 square inch hole, okay? So we've got 16 square inch hole, we've got 20 square inches we're leaking, which is the hole plus all the leakage around the fan and the cloth and this and that. So now what we want to do is to measure the background leakage. So we're just going to stop that momentarily, and we're going to take this slide back here and slide it down so that we have no hole. So the 16 square inch hole is closed. Now we want to measure the background leakage. And I know for a fact that it's going to be pretty tight, so I'm going to put the plug back in and measure it on what's called the L4 range. So I go over here and I change to L4, and I go set pressure again, 25. Let's give that a chance to kind of settle itself out. And it looks like it's settled itself out at 3.8, 3.9. So originally we got 20 minus 3 or 4 is 16, which is exactly the hole that we had in there. So this is a really fast way to check your blower door. You can do the same thing by using a panel up here with a 1 square foot hole, which will, at 50 pascals, would be roughly 1,000 CFM, but you can use whole flow on the fan in order to check it out, and we'll go through that later and show you how that works. So we're just going to stop that. So that's field calibration check on a blower door. What you can do is you can mount your frame in a room in a house or even a closet and put a piece of cardboard above the doorway and cut a hole in it and use that to check your fan. So we have a procedure for this for checking duct testers, which uses this calibration plate, and the flow rate is mounted right on the plate. This can go on the end of the flex duct, and it's a great way to check the calibration of your fan, or of your duct tester, I should say. Okay, so the next thing we're going to do is to take a look at a very fancy device, or unfancy, I should say. This is an exhaust fan box or a calibration check box or anything you want to call it, I suppose. It's just a simple box. I've got the end cut out, and I've cut it just short of the edge, so I've got a little bit of a flange here. Put a piece of weather stripping around it, and I've cut a hole in the end, which is exactly 25 by 25 inches. Five by 5. You can see it's kind of a rough hole. I just cut it out a few minutes ago. The flow through this hole is proportional to the size or the area of the hole. Okay, so we're going to try and use this in order to measure flow. So all we need to do is to measure the pressure inside the box, use hole flow on our gauge, and that will give us flow. So we go back to our gauge, and in this case we are going to not use this on the blower door at all, so we'll just disconnect these here. And we're going to take this blue tube, which is connected to that blue tube, and we're going to put it on the flow side. It should actually be yellow, but it doesn't really matter as long as you got it hooked up in the right place. And over here we're going to go to what we call hole flow. Change device, hole flow, 25 square inches, which is what that is. If it's different than that, you can enter it in here. Set that. So we're all set up for hole flow. So we've got this set up to EQLA. EQLA is a result that was a way of representing hole flow. We can also represent it as CFM if we want. So we've got that set. On this side over here, we're going to hook up our duct tester so that, let's see, we need some power. So these are the flow connectors. Hook those up. Notice we're in the depressurization direction. Okay, so here I'm going to set the speed. I'm just going to set it to about 45%. And I'm going to change this to, you can't see this, but this duct tester here is on the mid-range. So it's going to plop it back in there. So I'm going to measure flow in CFM. I'm set to the mid-range on the right-hand gauge. And liters per second, I'm going to change that to CFM. There we go. Actually, I decided I was going to do that in EQLA, didn't I? Okay. I'm sorry, I need to do this in CFM. My apologies. Okay, so we got this one in CFM. I'm going to go back and I'm going to change these units to CFM. Okay, of course we've got no CFM there at all. So on the right-hand gauge, it says we're blowing 75 CFM. So what we're going to try and do is we're going to try and measure that 75 CFM with this elaborate apparatus here. So again, it's a box. It's got a 25 square inch hole in it. We've got a pressure probe here that goes all the way around and goes into the channel B of this particular gauge. And all we're going to do is like set it up against this hole we have in the side, because this is the only hole we have in the system. The air is going into the hole, by the way. And you'll notice that we've got around about the same flow rate on our little flow box as we have on our duct tester. So you can say our duct tester is blowing 76, 77 CFM, and our little whole flow box is measuring exactly the same thing. Now, as nice as this is in the negative direction, having air flowing into this hole, it probably is not going to work so well on a supply flow. And how we're going to see that is we're going to take this fan and move it around like that, so we're now blowing into the box, okay? So we're blowing 79 CFM into the box, and we're going to push this back up to the hole again and see how well that measures. So you noticed before in the depressurization mode, we got pretty good results, but pressurizing this box, we're not getting anywhere near the kind of results that we got before. You'll notice that the results are bouncing around all over the place, and this indicates the problem with which we have of measuring supply flows versus exhaust flows. So supply flows are really tough to measure. You notice that we're kind of going in and out and all over the place here. So I'm going to try and measure that flow with a different type of device. This is called the Flow Finder, which is a new powered flow hood, which is a nice little device, and very, very sophisticated. And we'll see how it does in terms of measuring flow. So the first thing we're going to do is turn it on. And it's already set for CFM. And this is called a powered flow hood. So it has its own little fan in here that will run. It will get the pressure across this measurement hole to 0, so it's not going to influence the flow at all. And we'll see how it does. So first of all, we mount it on here. We press the go button, and it's compensating the pressure. It's bringing the pressure down to 0. And I don't know if you can see that, but that says 77.5 CFM. So you can see the huge amount of accuracy difference that we have between this box, which worked perfectly well under depressurization, worked really, really poorly under pressurization. The flow finders managed to get a result that's within 1% or 2. Let's just try it again and see what we get the second time. So I just put the flow finder on here. I press the button. I hold it. It takes about 8-10 seconds. It's compensating to 0. The little fan is spinning around. .6. So it's got two readings, virtually identical. This is a very, very accurate instrument, made in Europe, expensive, but it does a fantastic job. So I'm just going to turn that off. Maybe you can take, I don't know if you can see a close-up of that. There, I guess that's kind of hard to see. I can't really see that. You just have to take my word for it that this says 77.6 on this gauge here. Okay, so I'll set that down for a moment. So we're going to go back to the negative mode that we had before. Sucking air out of the box. And for your information, we've got a bunch of holes in here. All these holes are sealed off. These are sealed off. There's another hole in the top. It's sealed off. There might be a tiny bit of leakage in there, maybe a CFM here or there. So what we're going to do now is we're going to try a slightly different experiment where we're going to pull these holes out, again under depressurization, and we're going to see how well our little box does in measuring those flows. So again, we'll put this up, see if we can measure. So we got 34, 32, 33 CFM through there. And 58 CFM through there. So 33 and 58, we're around about, what is that, 90 CFM total. Let's just take another look here. 58. 57 CFM through that one. Around 30, so 87 CFM in total. It's actually doing a pretty fair job. But recall how much of a problem we had when we had a supply flow. So an exhaust flow is going to work fine. If we have a situation where there's some restriction and so forth, like with the plugs that we have over here, so we have two chambers in here that are connected together. So if we were to put these plugs back in, and then open up these two. Now let's try that. So we're measuring 49, 48, call it 48, and we're going to add this one on. 32, so that's 48, that's about 83. It's actually doing a pretty fair job of that as well. So whenever you're doing one of these, something that you have to bear in mind is that this hole has got to be relatively small compared to the holes that the air is going through. This hole is tiny, then we get a lot of pressure across here. So typically with these boxes, if the duct pressures are low, you only want to get like 5, 10, at the most 15 pascals inside this box in order to continue to get accurate readings. So I've covered most of the presentation that I was going to cover today a lot faster than I thought I would have, unfortunately. And so I'm just going to take a look and see if there's some questions here that I can answer. I'll just drag these questions out here. Okay, so there was a question asking about where was the blue tube in the box. Okay, so that one's pretty easy. Usually you want to have it on the plane about 2 inches from the surface of the box. We've got it in a corner which is away from turbulence and so on. So I just have a static pressure probe here. I just punch it in the side of the box. So that's all I have in order to pick out the pressure. Try to tangle all these wires. I guess that's why they made wireless. Okay, let's see what else we've got here. So somebody asked if the flow finder is a Retrotec product. Actually, it's kind of a combination. The flow finder body is something which is made in Europe, and Retrotec is going to be supplying the hoods that go onto this. The hood for this in Europe is $600, 600 euros. It's about $1,000, which is way, way too expensive for our market. So we're going to be making their flow hoods with these devices, and I believe this unit, as it sits here, is about $39.50. $39.50 US dollars. So Peter was asking why it doesn't work on a return Let's see. Why does it work on a return but not on a supply? Okay, the reason why it doesn't work on a supply is because of the jetting effect that comes out. There's a huge amount of turbulence which comes out of this hole when the air is flowing at it, so the pressure jumps around all over the place. So you'll always get good readings on returns but never supply because of the jetting effect. What this device does for jetting is it has a special chamber in there that neutralizes all of that in the front section of the flow finder, and then it measures the flow in the back end. Every other device on the market, the flow and the pressure neutralization and pressure stabilization are in the same area. So what they've done is they've separated it into two areas, and that's why this thing works so well. It's also the reason why when you use a flow hood or a passive flow hood that you'll get the air coming in from the flow hood and sometimes circulating around and sometimes passing the flow sensor several times before it goes anywhere. And a really good way to see this, if any of you have a duct blaster, just take it, put it on the floor so it's on its back, and turn it up to full speed. It measures 850 CFM and there's 0 CFM going through it. It's a really good example of a situation where the air is merely going around in circles, and each time it goes by, it assumes it's gone past for the first time, but it's not going anywhere. So that's a problem you have with jetting. These jets come in, they circulate around, and they upset the flow measuring apparatus. Somebody said, what happens if you don't use the probe? I'm assuming that's what he said. You can just take a tube and shove it in here. What's nice about the probe is that it's not affected by velocity as much. It will be more stable, and it allows you to punch it through the box, which is kind of nice. But you could just put a tube through there. Sometimes if you use tubes, you might want to put it at a couple locations, but normally a tube through the box in this area, which is very stable from airflow, the tube goes through the box in this corner here, it usually will be fine. However, if we have supply flow and air is blowing at it like this, it'll go even crazier than this one did. Those probes are not expensive. Now, as far as experimenting with probes, no probes, that kind of thing, this is something you could do yourself if you have any flow measuring device like a duct tester, blower door, or whatever. You can create your own boxes, you can cut holes in them, and you can do a comparison between what hole flow shows on our gauge, which could be a DM2 or a DM32, and you can see how that compares to the flow you're supposed to get. If you have another make of gauge, there's a formula that you can use that says CFM is equal to the square root of the pressure across the hole times the area in square inches times 1.075. Okay, so CFM is equal to the square root of the area, the square root of the pressure in pascals times the area in square inches times 1.075. So for those of you who don't know what square root is, square root of 25, for example, is 5. 5 times 5 is 25. So the square root of 25 is 5. The square root of 49 is 7. So if you're doing it at 50 pascals, you take the square root of 50 is about 7.1 times the area times 1.07 equals the flow. So somebody asked, does the exhaust fan flow meter work similarly? Exactly the same principle. It's a principle of physics. Nobody owns it. All that an exhaust fan flow meter is a box with a hole in it. So if you want to create your own dish pan and stick a hole in it, as long as that hole is a known size, there might be some slight variations in the calibration of it. But as you've seen here, we got our result within a couple %, which is pretty good. So somebody was asking me again about the difference between a Pitot tube and measuring duct pressure with a static pressure probe. So a Pitot tube, which is this device here, will actually have a positive pressure. See if I can find a piece of tube here that I can stick on it. will actually create a pressure when it's in an airstream. I don't know if I can force one of these tubes on here because it's see if I can get one on the end here. No, I think this is way too big. Usually we put adapters on the ends of these things so we can get the tube on there. But if I was to hang this into the airstream like that, I could actually measure the velocity. So what I need to do to measure flow with this is measure the velocity times the area, and it's pretty complicated. Very few people do it. You can do it in ducts and so on. So it's a pretty fundamental tool, but it's one that requires a fair amount of skill. So it's measuring velocity. So flow is equal to velocity times the area. So that's the reason why we have these flow devices, so we don't have to bother with that. Taking a good pitot flow, using a pitot tube on a duct of this size, you might spend half an hour doing that, So if you have a flow device that we can use, like we're talking about here, we can do that much faster. Okay, I think I've got most of these questions answered here. See how we're doing time-wise, 42. If any of you have got any comments, you can put comments on there. If you've got questions you want to ask us. This was a lot more popular a webinar than we'd thought. We had another one on earlier this morning, so we were a little scrambling for time to get this one organized, so I apologize for that. But if it's something you'd like us to focus on and talk about some more, we'd be more than happy to do that. I think I've handled all the questions here. So somebody asked, can the flow HUD flow finder be used to measure the extract fan ventilation rates for standard extract as well as mechanical ventilation heat recovery systems? So this little device here will measure flow rates balanced to zero pressure balanced flows up to 330 CFM, unbalanced to 850 CFM. We currently have a hood that will fit on a 2-foot by 2-foot register. We plan on making bigger hoods than that, so you could do commercial or residential, and it goes down to 3 or 4 or 5 CFM. One cool thing about it is that if you want to measure supply or return, you just put the device on the same way. It knows the flow direction and will work on supplies or returns, and you don't have to turn the device around or make any adjustments in any way. So it's a very sophisticated unit. We weren't able to see that here, but one of the things that you will notice when you're trying to measure pressure across these holes, that the device itself will actually influence the pressure in the duct that you're trying to measure. So the reason why you have a zero balance on there is to eliminate the insertion of the device itself. So if you compare this to let's say a flow hood where you've got a passive flow hood where you've got, let's say, 3 return openings. The moment you put something over one of those openings, like a passive flow hood, the air will now flow into those other openings. So what this does is it neutralizes the pressure to zero, so we can actually measure them independently, and the duct system doesn't know it's there. The only problem with it is expensive. Somebody asked if this could be used to measure outside air CFM. Essentially, anything that you can connect this up to, you can measure the flow of. For example, we could take a great big huge box and we could stick this on the box, and we could put that box over something else if we wanted to. This unit, well, in this configuration, we could put 300 CFM through there, and we could still neutralize that to 0. It has its own neutralization fan in there that operates. It pulls the pressure across this hole back to 0. Okay, any more questions? The length of tubing making a difference? No, it does not, unless there's a leak in the tube. We've tried as much as 1,000 feet of 16th ID tubing, and we didn't notice any difference at all. The only time that makes a difference is when there's flow through the tube. But when the gauge is hooked up like this and the connections are tight and there's no leakage in the system, the length of the tubing doesn't matter. It matters more with analog gauges, because with analog gauges there's a diaphragm in there, and to go from, say, 0 to full scale, we have to move a fair bit of air, like maybe, well, I don't know, say the volume of my phone almost, worth of air through the tube. That takes time. With these gauges, the diaphragm is minuscule. It's just, I don't know, like a few thousandths of an inch across, and no air at all has to move in order to push the gauge through full scale, as is demonstrated by the fact that I just touch my finger on there, just barely touch it, and the fact that a little piece of my finger is just squishing inside that hole is causing that gauge pressure to go up quite a bit, as you can see. I push my finger on there and it goes up 160 CFM. So the volumetric change inside the tube and the gauge is very, very small and produces a big pressure change. This flow hood is, with the kit as you see it, with a carrying case and so on, is $39.50 US. Now, someone said, is my blue tube in the yellow port? Actually, it is. It should be a yellow tube. The color coding of the tubes is meant to remind people to plug them into the right place. And yes, I probably should have used the yellow tube, but I grabbed the wrong one. But with the systems that we put together, we only put the right color tubes in there, so you won't have that problem. It just makes hooking it up correct, or they're much less liable for error. If you're interested in the flow device, just send us an email, and we can send you some information on it. It's called the Flow Finder 2. The original Flow Finder is probably 15, 20 years old, and this is the newest powered flow hood that's on the market. I liked it in particular because when we pull this off, we have to have this on for supply flows, but on exhaust flows like a kitchen fan, I took a look at all the devices that were out there that were used to measure kitchen fans and so on, and I couldn't see how any of them could fit underneath the range hood. But this is all you need to get under the range hood. In fact, you can just hold it with one hand. And because it's powered, if you have a little bit of leakage around here, it doesn't matter, because it will neutralize the pressure on this plane to 0. And even if you make measurements where there's a pretty big gap, it'll still give you a pretty accurate result. So I'm going to just do a little demonstration here. Let's see, we're on exhaust mode. So let's say this is an exhaust fan. I just pressed the little button, and I don't know if you can see the fan spinning there. I don't think you can. Maybe just in the corner there. So it's now I'm not measuring all the flow. I measured 53 CFM, but I notice I've still got some flow coming out these holes over here. So I'm just going to plug those up temporarily so I can measure all the flow. There we go. Okay, let's try that again. Just press the red go button. So it's neutralizing to 0. 79.5, that one's saying 74. So now what I'm going to do is I'm going to just open up the slide. You can see I don't quite have it in contact here. I've got just a little bit of an opening just so that you can see. That's the size of opening I've got there, and I'm going to try measuring it again. Seems to be having a hard time finding 0. Maybe it knows I've got a gap there. Okay, let's just push it down, see if that does it. Okay, so I'm going to try this again. I'm going to try it up tight. $80 CFM. Now I'm going to open it up. $86 CFM. So you can see the gap there. I got 80 CFM, 86 CFM, pretty close for the pretty huge gap that I had in there. So we're talking about a very sophisticated instrument. I think they've been developing this since 2008, so it's not something that they dreamed up yesterday. Okay, let's see if I got any more questions here. So Rochelle was saying, from what I've shown, that the fluid doesn't have to cover the exhaust area completely. For example, on a large kitchen exhaust range, that is true to a large extent. You should experiment with it just to get clear on that. But I've actually done things like, and I'll do it for you here, where I'll just take half of the hole here, and let's see, just trying to get half that's open on the inside. I'm going to measure half. So that's 50. Now I'm going to measure the other half. So I'm actually measuring half the hole at a time. I got 49, so I'm a little bit off. I got 50, 50. I've roughly about 100. But you'll see I had only half the hole covered up like that. I don't know if I had it exactly at the halfway mark. So I noticed in doing a house the other day with this that there was a big return, and I actually measured the return in 4 separate pieces, and I got a result that was pretty close. There's nothing out there that will do this. The reason why it can is that it has a pressure zeroing sensor in here that's accurate to hundredth of a Pascal. It's a very special type of device which has particularly good results around 0. And the typical gauge, like our gauge or the Energy Conservatory gauge or anyone else that makes these high precision gauges, around 0, they're accurate within 0.15, 0.2 at best, 0.2 pascals. So this is probably 10 or 20 times more accurate in terms of zeroing, which allows us to do some pretty exotic testing with it. Okay, I think that we're pretty well done with most of the questions, so I thank you for your patience, and I do apologize for screwing up, not knowing that my gauges were hooked up wired as opposed to wireless, but I think I was able to recover fairly well. And I would like you, if you've got a gauge and you've got a flow measurement device, find yourself a box and play around with it so that you can try out some of these concepts.